Okay, did you understand this part?
Right, sir.
What did you understand? So did you understand the first part? Or so it's like this, right? It's like this. Let me show you this graphically. Then I think you will understand, right? This is stack point SP. Right? Initially the SP here, according to this one, so my list is this one, which it's having like, so let me create this using a table, then I think it will be more clear to you. But if not, right, let's create something using shape. My list is something like this. It has 5 items: 1, 2, 3, 4, and in my list you have altogether 5 items, something like this. Okay, that's what happening here, right? The first call. My list has 5 items. And the stack pointer is,
Yeah.
yes, what is the value of stack pointer? It's -1. Understood that or not?
Yeah.
Right? That is minus,
Yeah.
stack pointer is -1 is here, right? Because this one is 0, you know. This one is 1. The next one is 2. This one is 3 and this one is, sorry, this one is 3 and this is 4. Right? You know how indexing work, right? In an array or list, it starts from 0.
Yeah.
Right? This is 0, 1, 2, 3, 4. These are the indexes. The last item is 4. -1 is it is not there in the list. It is out of list basically. But when you add an item, when you push an item, what you have to do? When you push the first item, so you have to check if the stack pointer is less than my list -1. My list -1, my list length is 5, 5 minus 1 is 4. So altogether the value here is 4. Understood?
Yeah.
5 minus 1 is 4. Right? It checks whether SP is less than 4. Less than 4 means it can be -1, 0, 1, 2, 3. No? Less than 4, no? That
Yeah.
means your stack point is somewhere here, 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 or here. Right? It is can be
Yeah.
-1, can be 0, can be 1, can be 2, can be 3 maximum. Because less than 4, no? Here, right? So let's say the maximum, if it is 3, then what it does, it first increase the value. First it increase the value. If it was 3, increasing will make it 4. Then you will tell, okay, the 4th item is the item. Now you insert here. Understood?
Yes.
Right. So why I'm checking whether it is less than 4? If I check it is less than 5, then here will also be counted. Less than 5 do not, 4 is also valid. Then SP is SP plus 1. Then it will go to 5 and try to insert. But can you insert there? That is out of
No.
the list, no? If it was like this, if I remove this -1, then it will try to insert even when this is less than 5. Less than 5 means 4 is also valid. Let's say stack pointer is here. Now you are going to increase the stack pointer by 1. Then stack pointer will become 5. It's out of stack because the 4 is the last item. Now stack pointer 5 is equal item. Can you do that? Can you do that? Yes?
No.
Yes, we can't. Why? Because 5 is out of this list. For 5, you can't insert. You can insert here. Let's say you can insert, if it is -1, increase in 1 and you can insert here. If it is 0, increase in 1, you can insert here. If it is 1, increase in 1 will make it 2, you can insert here. If it is 2, increase in 1 will make it 3, you can insert. If it is 3, increase in 1 will make it 5, you can insert. But after that, can you insert? You can't insert because it's exceeding the stack. So here, else we have to tell, okay, else maybe you can tell error print, you can print stack is full. Stack is full. Okay, let's try to do this and see. Okay, let's try to practically apply and this and see. I'm going to run this. Run module. I'm going to run this. Okay, then let's push. I'm going to push item 23. Now it's in the stack. Oh, I got an error. What is that? Local variable. Here I have to tell this is same stack, right? Global SP. That means referring to the same SP here. Otherwise, this will be treated as a local variable. Right? So let's say run it again. Oh. Sorry, global GLOB. Yeah, I'm not sure what is. Yes, global GLOBL. Global SP. Okay, now it will not give that error. Let's push 23, accepted. Let's push another item, push 27, accepted. Push 270, accepted. Push minus 34, accepted. Push let's say 90, accepted. Push, I'm going to push 89, rejected. Why? It says list index out of range. List index out of range. Understood?
Right.
Yes, understood. And this is what, yeah, this is the issue. This is the issue. Then we can print the list, my list. Let's say my list. You can see all the, all the items except 89. Why 89 was not inserted? When my list SP equal item, it says this is out of order. You are checking whether this P, right? SP is less than, SP is less than. So the SP initially -1. Right? -1 is less than this. Yes, accepted. Increment at 1. Now it's 1. The second round, let's print the SP also, right? So this has an error since, so let's print the SP also. Let's print the stack pointer 2, just to understand. Run it again. Let's push these items again back. Push the first item. Now you can see stack pointer is 0. Push the second item. Now you can see stack pointer is 1. Push the next item. Now you can see stack pointer is 2. Push another item. Now you can see stack pointer is 2. Push another item. Now stack pointer is 4. 4 is less than 5. Yes. Therefore, it will try to increase again this to 5 and try to insert. Right. So this is again, I'm going to push another number. Now it will give an error because invalid index. That's why I said you have to check this -1. Because otherwise it tries to access the 5th position because 4 is less than 5. Then SP equal SP plus 1 will be 5. But if you're trying to assign this to 5, it will be giving an error. Now let's try after assigning -1. Now let's try to do the same. Okay, I'm pushing the first item, accepted. Pushing the second item, accepted. Pushing the third item, accepted. Pushing the fourth item, accepted. Pushing the fifth item, accepted. And I'm pushing the sixth item. It will say stack is full without giving that ugly error. Can you understand why I put -1 now?
Yeah.
Because after checking only, this will increment. If it is checked and incremented, then that will be a problem. If it is 4, if this is 4 and this is 5, it will go inside and it will increase. Now 5, but you don't have 5th item in this stack. So stack is full. Right, now it's giving this error without giving this ugly error. So that's why I have used push. Okay, I think you can now tell the pop. So how to get the pop? Pop means removing from the stack. You remove item from the stack and return that item. Right? Remove item from the stack and return that item. Okay, again I'm referring to this global stack pointer. Same stack pointer. I'm referring to the same stack pointer. So okay, so last time you can see stack pointer is now in 4, no? After inserting, now it's in 4. Can you remove item from the fourth index? Is it valid operation? Can we remove item from this cell? Can we remove item from this cell? Is it a valid operation? Yes? I need your answer. Come on. හතරවෙනි index එකෙන් අයින් කරන්න පුළුවන් item එකක්. Can we remove? Yes. Is index 4 is a valid index or not valid? Index 4, is it valid or not valid? Siddhas, can you hear me?
Hello.
Can you hear me?
Yes, sir.
Okay, is that fourth index valid or not valid? Can I remove item from fourth index?
Yes.
Yes, possible. So be confident about your answers. Don't give doubtful answers. Like it's possible. You can remove item fourth index. Fourth index is valid. So if so, is it -1? Is it valid index? -1, is it valid index?
No.
No, it's not valid index. So here again you have to check if stack pointer equal to -1. Right? If you are asking remove from -1 stack pointer, then you have to tell you can't remove the item, so you have to tell print stack is empty. Agree? Stack is empty. You can't remove because it's empty. If it is -1, means it's empty. Else, if not, just you can remove.
Yeah.
Else you can remove. You can remove the item, which is you can return the item. Return the item, maybe return the item stack pointer. You can say my list and the stack pointer you can return because it's valid. And after returning, here actually you have to return after giving this error, you have to return. So return -1 because it is not valid operation. So here return the stack. Then at the same time, what you have to do, return the stack pointer. At the same time, what you have to do, you have to say stack pointer equals stack pointer -1 because after removing this item, stack pointer should move down and point into the next item. Understood? After removing this item, stack pointer should move down and refer to the next item. So you have to tell that stack pointer equals stack pointer -1. Okay, now let's see how this is going to work. Right? You're going to return this. Or here you can say without returning this, you can say return value equal -1. Here you can say return value RV return value. Initially the return value is also -1. So RV equal -1 in this case. Here RV equal my list P. Then finally after all these you can return value. Because here in case of stack is empty, it's -1. In case stack is not empty, it will return the item and reduce the stack pointer, and that is your RV. Right, okay. So let's run this code and see whether this is accepted. I'm going to push 23, push 27, accepted. push 270, accepted. If I pop now, what will be the value? If I pop now, what will be the value that I'm going to get? Yes?
90.
I have inserted 23, 27 and 270. Now those are the values in stack. How come that 90? 90 is not
Oh,
inserted.
so 27.
27 or 270?
27.
Why? You know how stack?
Because you're removing.
No, I'm asking what is the value which is going to remove? I put 23, then I put 27, then I put 270. Then I'm removing. What is the value I'm going to remove now? What is the what is the value I have removed?
270.
270, yes. It is the last value. It is 270. I'm popping again. Now what will be the value? I'm popping again. Now
27.
27. And I'm popping again. Now 23, the last one.
23.
Yes. You know the last in will be the first out. Antima time danakena thamai salam elitian. Now I'm again going to pop. Now what will be this?
Right.
Can I pop again? Yes.
No.
No, then it will say stack is empty and it's -1. Stack is empty. Oh, without returning this -1, I can tell RV is empty. Empty. So it will not return anything. Right?
Mhm. Yeah.
Okay. So let's say I'm going to do that again. Push, 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 and I'll push this one, and I'll push this one too. Now I'm going to pop. What is the value that I'm going to pop in? Popping out
90.
90. Then
Minus 34.
34. Yes. Then 270 and then 27.
270.
Okay. Now, did you understand the concept of stack? So this is the concept that we learn, no? What we have to do? So when we learn
Yes.
in programming, actually, learning the concept not enough. You have to implement the concept. And this is the implementation. Is it clear now?
Yeah.
Is it clear now?
Yeah.
It's still hard. So maybe the first time you will feel hard, but you have to understand, right? Okay, now it's working as stack,
Yeah.
but the stack maximum limit of the stack is 5. Right? You can manually change this. You can make stack size 10. Just multiply this by 10 and it will create stack of size 10. Right? So that is simple.
Mhm.
Or uh, you can use another one, another method, right? Let's say another method. You can say def create stack, create stack, def create stack. In this one, I can tell, okay, my list equal empty initially, but here you can say count. Let's use count. Here you can refer to the global my list, and here my list equal this empty list into count times. Now this is more smart. Now this is more smart. Why? Because when you run this, now you can create stack. Create stack. And you can give the size of stack. Let's say size of stack is 6.
Right.
Yes. Now you can push how many times? Push 23, push 2, 3, 5, accepted. Let's put some other value, accepted. Let's put some other value. Accepted. Let's push some other value. Accepted. Let's try for some other. Accepted. Now you already have put 1, 2, 3, 4, 5, 6. So let's try to push another value. Rejected because size is. Now you can create your own stack, okay? Because there's another method to create
Yeah.
stack with your defined size. Understood? Right? Likewise,
Yes.
you can add any number of, maybe if you feel then what if you want to extend the stack. If you want to extend the stack, that means you need another method to extend the stack. Extend the stack means in the middle you need big stack. So you can extend this. So you can use another one, def extend stack. You can say num or extra count, extra count. Then you can say extra count. You can calculate the length of the current stack. C equal length of current stack. My list. Calculate the length of current. So these are actually, this is flexible, right? I know these are not there in the normal stack, but you can create your own one. Length of this. This is the original size. Then the
Right.
extra count you are going to add. Right? Then total count TC equal original size of the stack plus the extra count plus the extra count. Original size of the stack and the extra count. Now you can create a new stack.
Yeah.
With, yes, you can create a new stack with this count. TC total count. Now the stack size will be, yes, now the stack size will be increased. But the problem is what? It will become empty, no? Because you have added few items, now you need to extend the stack. But this will
Yeah.
make entire stack empty. So how to stop that? Right? You have to keep the current stack, right? Keep the current stack. Maybe you can say values, values, or stack values. Stack values are the values in this one. Stack values are the values in this. This is what you have used. You have asked the question like how to swap two variables. Likewise, you can keep the stack values in some other new stack. Now, after creating this stack, I can say 4, and you can even keep the stack pointer. You can even global stack pointer. You can keep that stack pointer too. Right? You can say, okay, for v in stack values. After making this empty, you can say for v in stack values, you can add this. You can say my list dot, for my list, you can say the index is 0. Let's say I equals 0. Or you can say while I less than length of the stack values, my list dot I equal my list dot I equal stack values dot I. That you are going to add these old values to the new stack. But anyway, user will not see all this complexity. But user will just extend. But when extending, what will happen? Then you have to make this I equal I plus 1. So let's see, it can be error. Let's see whether this is working. So you have to understand these codings, right? So what I have done, understand the concept. No need to do this from the beginning, but just understand the concept. That's enough for your level. What I have done,
Yeah.
I need extra space. So I have extended. When I extend, what will happen? When I extend, what will happen? So I created this. I have taken the old count and added the new count, and I have taken the total count and I have extended the list. But it has make everything empty. Before doing that, I kept the old values. Starting from 0 to the end of the old values, I have added these values one by one to the new my list. So I have preserved the values I got. Okay, let's see. Let's see. Still, I'm also doing this first time, right? I'm also doing this first time. Maybe I can also generate errors. So here, one error.
Right.
Let's find this. Because I just thought, why you can't extend this? මම කියනකොට මට question එක කියනකොට මට හිතන දෙයක් තමයි why, so there should be some flexibility to expand this stack. So but that is not that. By default you have push and pop only, yeah? Push, pop and peek. You don't have extend stack, create stack. Those stuff are not there. I just added. Okay, let's create a stack of size 3 now. And I'm going to insert, push to the stack 23, accepted, push another value. Let's push this value, accepted. Let's push this value, accepted, 3 values. Now I'm trying to push 99 and it says no, stack is full. Oh, poor me. So I need to extend this. Extend the stack by adding 3 more items. Okay, return with nothing. I don't know whether everything's successful, but I can check my list. Hello, my list. Yeah, I can see here initial values are still there. It has extended by giving 3 values. Lucky me.
Oh.
So now you can see, you can add. So that is what programming is, that's right. Programming is, you can't define this is the end of programming and now you have learned everything. Likewise, nothing. So it's just implementing the concept. What you think, if you can implement that using the computer language. So that is programming. That is interesting, but need to put some effort.
Yeah.
Right, you need to put some effort. You have to worry how to do. If I do something like this, I have just used your fundamental theories, nothing else. But the logic should be there, right? The logically what should happen, it should be there. Okay, I have extended. Now I'm going to push some more items. I'm going to push this item, accepted, push this item, accepted, push another item. Okay, let's push this one, accepted. Okay, now I'm trying to push another item. Now I'm trying to push another item. Now again stack is full, right? Because now everything filled. New items that I have put, it's in the stack. 100 you can't put, but still you can extend because you are lucky. You have a function to extend. If space is not enough, you can extend. So see here, this is a practical problem when partitioning hard disks. Earlier days, if you have partition, can you extend the hard disk partition? Hard disk එක partition කරනවනේ දන්නවනේ C D විදියට බෙදන්නේ. You can divide this to C drive, D drive. Yes. At the initial stage,
Yeah.
you can press Windows key and E key if you are using a computer. Windows key එකයි E key එකයි press කරාම hard partitions ටික පෙන්නනවා. But earlier days, it was not possible to extend. When hard disk is full, you did not have any other option other than deleting the existing partitions and recreating the partitions, but it will delete all the data. But if you delete the partition and recreate that with more space, it will delete those data. But new Windows versions are supporting partition extensions. It is possible to extend partitions by acquiring some empty space from other disks. So that is very good, no? Because no need to delete, format, no need to
Yeah.
retreat partitions. Without that, you can add the space. You can add the space from other partitions. So that flexibility is there in the new versions of Windows. But earlier versions, it was not there. So see, the same theory applied, no? Same way, what they have done. But that is complex because if more data in hard disk, you have more data. Extending is not a simple job like this because all the data, you have to preserve all the data and add it at the balance space. Right? So, but anyway, that is
Yeah.
supported now. That feature is there. So that is complex program, but still that feature is there. Okay, then peak. So this is extra function, right? This is not there in the stack. Don't worry, this is extra function. In case if this stack struggling because it is full, then right, then it will allow you to extend because of this function. But this is extra added by myself. It's a bonus. Def peak. Okay, let's access data from the top of the
Right.
stack. That is simple. What you have to do? You have to return. Okay, you have to get the global same my list, and from that return my list the stack pointer item. The stack pointer is also global. So you are going to return the stack pointer. That's all. Nothing to do. No need to change the stack. You are just accessing without removing. You are just accessing. Let's see. Let's on this. Let's push few items. Push this one. You have to before pushing. You have to create a stack, right? If you try to push this, it will give an error. Stack is full because it's already empty, right? So you have to create a stack at
Right.
least with few elements. Create stack. Now you're going to push 23, accepted. Push 100, accepted. Push 98, accepted. Try to push 77, but not accepted. It's full. Let's peek. When you peek, it says 98. If you peek again, what will be the result? Peek again.
100.
That is in pop. Peep will not change. It will access the item only. It will not change the stack pointer.
Hello?
So still you'll get 98. So see the difference, right? Pop will step down. Pop will remove the item and step down to the next one. But peek, it will just access. If you peek again, again 98. If you peek again, again 9. But if you pop, 98 will be removed. Now if you peek, now it is 100. That is true, right? So be careful about peek and pop.
Right.
Okay, shall we copy and try
Yeah.
the same? So this is lengthy, but I think you should try this, right? Even though this is lengthy, you should try to, because then only you will understand this clearly. Please try this. I'll give you extra minutes. Please try.
Yeah.
So reverse polish notation is basically, that is what the notation used in stack, right? So here, normally we use A plus B into C. But in RPN, the reverse polish notation, so we write A, B, C, asterisk and plus. So what is that? So what we do, actually we push A, push B, push C. So think about the
Right.
step, right? That just we learn. Push A, push B, push C. Then you multiply. What will happen when you multiply? The nearest two items will be multiplied. That means the last inserted is C. C and B will be multiplied. Right? C and B will multiplied and it will become a single one. So if assume that's okay, A is 1, B is api to mein, A equal 1, B equal 2 and C equal 3. Then BC multiplied 2 into 3 is 6. Now stack pointer will store 6, right? So when you put plus, it will add 6 to 1 and the result will be, yes, 7. So in stack, we are using reverse polish notation to do the calculate. This is called reverse Polish notation to do the calculation. No need of brackets. No need of brackets. For an example, okay, let's use the same thing and understand this. Let's use the same concept and understand. Okay, let's say in stack you want to add, okay, this you want to add 5 plus 6 and multiply by 3. What is the answer? 5 plus 6 multiplied by 3. What is the answer? Yes?
33.
5 plus 6 multiplied by 3. What is the answer?
33. So
Yes, 6 into 33. Oh. No, first multiplication will happen, no? Because you know the
oh,
what?
sorry.
First it will be,
Yeah,
so let's put brackets.
23.
Now we can, anyway, without brackets also first multiplication. First will be the multiplication, right? Multiplication will happen first. And
Yeah.
so then the answer 6 into 3 is, yes, 6 into 3 is 6 is 18 plus 2, sorry, 18 plus 5 is 23. Right? In reverse
23.
Polish notation, what you do, you push 5. So let's say this is the stack. Push 5. So 5 will be here. Then you push 6 and 6 will be pushed to the stack. Then you push 3. Push 3. Then 3 will be there in the stack. What you have done, push 5. Sorry. What you have done, push 5. Push 6. Push 3. Then you multiply. Then multiply. What will happen then? 6 and 3 will, when you multiply, it will happen from the stack top. Ne? Stack top again, even operation, stack top will multiply. So 3 will be multiplied by 6. What is the value? 3 into 6. Yes, 3 into 6 is 18. So stack
18.
top, yes, nearest items in the stack top will be multiplied. Then 18 will be the answer. So stack top is now 18 because 3 multiplied by 6. It's 18. Now you add. Now you add. When you add, 18 plus 5 will be added. So answer will be 23. Did you understand that? What is reverse Polish notation? In normal notation, in normals, this is infix or infix notation.
Yeah.
So you use the bracket to multiply and then multiply, then add. Lot of work, but in stack it's very easy using this reverse Polish notation. You push 5, push 6, push 3, multiply, the nearest items will multiply, then add. It will give the answer, which is 23. Now, if you pop, 23 will be the answer. Or if you peak, 23 will be the answer. So adding and multiplication, I didn't put that to the stack. But if you want, you can put that to the stack operations, like adding and multiplication.
Yeah.
Okay, right. With that, right, this is so then you can, so these, there are some practice questions to write in the reverse Polish notation. Please use that and write in reverse Polish notation, right? So here, so what will happen? A plus, so it's very easy to do. Using a tree, you can represent this. A plus B, here, A plus B into C. B into C separately, right? A plus B into C. Then how you write is basically, first you access A, then B, then C, and then, so if I draw, this is called, which traversal this is? We have not done trees, but there's a name for this traversal. You start from this and go like this, then go like this, then go like this and come forward. First you will be accessing this item, then you will be accessing this item, Then you will be accessing this item, and this item. Right? So then what is the order? A, B, C, asterisk, plus. Here, A, B, C, asterisk, plus. That is the reverse Polish notation.
Right.
You write as a tree and then access like this. So this is called which traversal? This is called post-order traversal. Still, we have not learned the tree data structure, but remember this word in post-order traversal. Post-order traversal means you go, but when you turn, you read the element. You are not reading the element when you are going, but when you're coming back, you read the element. Yeah. Going forward, yeah, you are not reading the element. But when coming back, you read A. Coming back, B. Coming back, C. Coming back, asterisk. Coming back, plus. So there are some other pre-order traversal. Pre-order traversal means you read while you so when you visit, as soon as you visit, you read it. That means you have same A plus, but that cannot be applied here, right? And asterisk multiplication B and C. There's some other traversal that is related to tree data structure, right? Make a tree data structure ki kaya, but I'll explain you. That is not a big thing. So when you go and read the element like this, then it is called pre-order traversal. You read plus first, then you read A, then you read this asterisk, then you read B, then you read, sorry, yes, plus A, then B, sorry, plus A, B, asterisk, then C. So this is some other traversal. But this is not going to be used in tree as in reverse Polish notation. In reverse Polish notation, you use post-order traversal. Then post-order traversal, pre-order traversal, in-order traversal. You have three kind of traversals, but still we have not learned. But remember the wording and how it happened. So I think better you draw this and show, right? So in stack we do reverse Polish notation RPN. In stack we apply RPN, reverse Polish notation. And how it applies, you can see this. Reverse Polish notation means you make a tree and read in post-order traversal. Here you can see so how stack operations are applied and after each step. So this is a visual representation of stack. And actually in the chapter 2, so implementation part is not given, but so we have even discussed the implementation part, but here the operations mainly what are mentioned here. Yeah, that part is not really mentioned here. So let's move to the data structure part. That is there in chapter 23, I think. The data structure part. Stack is referring to many words, as I said, right? So in networking also stack use, and maybe in the development there are something called full stack development. They are also stacked here 23. So it has more about this data structure in computational thinking. Here you can see this is basically for sorting and searching. We did that. And stack. Here also there's a given, this is stack pointer and base of the stack. Basically, we discuss about that stack point, how it is maintained and all. So this can be actually created by using a linked list or array or a list. You can use a linked list or array to implement stack. Actually, we have done this using an array, actually, not an array, but using a list. But there are some other methods to implement the stack. Using linked list also, you can implement. But here, mainly it's focusing about the theoretical parts, right? Mainly it is focusing about the theoretical parts, and implementation, actually, you have to try with the idea. And let me give some more explanation to the next one, which is queue. And the main difference between queue and stack is basically stack will be last in, first out. Whatever you insert last will be taken out first. That is LIFO. But when it comes to queue, it is first in, first out. Basically, you insert to the front, sorry, you remove from the front and you insert to the rear or the back end. The first item will be in the front. A is the first item and B is the second, C is the third, D is the fourth, and E is the fifth. You insert items to the back and you remove the items from the front. So for an example, you can insert item to the back, and when this queue is full, what will happen? Let's insert E, then F and J and H, E, F, G, H. Then queue is full. So let's remove items now. A is removed, B is removed, C is removed, D is also removed, E is also removed. Now front will be somewhere here. After removing 5 items, A, B, C, D, E, front will be somewhere here. But back will be pointing to here. This is the end. So now this is incorrectly telling that the queue is full when you try to insert items, but it has come to the end now. When you try to insert the item, it has come to the end. So it will blindly tell that queue is full, but actually is it full? Or is there some empty spaces in the beginning? Because you have removed these 5 items, these 5 items are empty now. But since your rear is here, the back is here, it will tell, so I have come to the last item, so no, we can't insert more items. Since you are removing from the front. Therefore, there's something called circular queue. Circular queue means after removing or after inserting, you will again go and try to insert to the first place, because then rear will be pointing here. Normally rear is going down and end here, that is normal queue, but in the circular queue, rear will check whether it can access the elements here. Then it is saving some space. That is called circular queue. Right, let me show small animation on this. Okay, in this one, basically, so these are the queue operations. Let me show the queue operations first. So if you want to insert item, I want to insert tree, I'm going to end queue this. This is like in stack, it is push now. This is called end queue. Okay, the first item is end queued. So now you can see head is 0, tail is 1. Let's end queue another item. Now tail is 2. Let's enqueue another item, 56, enqueue. Okay, let's insert another item, enqueue. This is how it's inserted. When you dequeue, removed. Now head is pointing to 1. When you dequeue, removed. Now head is pointing to 2. When you dequeue, removed, removing from the front. When you dequeue, okay. When you dequeue, what will happen now? When you dequeue, what will happen now? Now head equal to tail. So no more items to remove. So it will not dequeue because no more items to Now you can enqueue. Let's enqueue another item. It will be added to here, but there are some free spaces, but those free spaces will not be used. So that is the issue of this standard queue. Did you understand the issue?
Yes.
There are some more items, but still, so some free items, but still you cannot insert to that due to this head and tail issue, because it's not going to take that space in the beginning. Let's enqueue all and see. Let's enqueue some another. I have saw a few locations. Enqueue again. Enqueue again. I'm trying to enqueue. I'm trying to enqueue. Okay, this is what happened in the circular queue. Understood? So it will increase the tail and enqueue. After 14, it will again come to 0. Then again enqueue. Again you can enqueue. This is called circular queue. But now there's a problem basically because I'm going to enqueue now, but it will create a conflict because then tail will be equal to head. So if tail is equal to head, then that will be a problem. So it will not use this space. Tail here, when tail is 1 less than head, when tail is 1 less than head, it will assume that, okay, now my queue is full. I have to dequeue and then you can enqueue. Right? So this is how it goes. Okay, what you have to do, now I have done the visualization. What you have to do, actually you can do this as a homework. But so try to implement queue. So I know it's not going to be easy. The code is even not there in your book, right? But you can anyway find a code from internet. But the thing is, I don't mind if you find code from internet, I don't mind, but you have to give a try. Try to do this alone, similar to how I did. It's okay to fail. Failing is the best thing because failing will give you new question. One failure means one question. Two failure means two questions in the exam. Three failures means three questions in the exam. Likewise, if you fail and fail and fail, you will learn a lot. So you will be able to answer many questions when you fail because you know how these failures happen. Why you fail? You know the correction methods also. Therefore, don't be afraid of failures. Okay, then with that, I'm going to stop for today's discussion. So try to implement queue. So then next day we'll discuss about other data structures like tree, hash table, hash list, and linked list. So let's discuss those things next day, maybe
Sir,
tomorrow.
are you available tomorrow, sir?
Yeah, tomorrow we can, I think tomorrow, but the thing is, tomorrow we have to allocate a time in noon or morning. So morning, I'm not sure. I'll give you a time, right? I'll give you a time. In morning itself, I'll inform the time. I'm available, but not after 5. After 5, I'm having another class.
Okay. So because in the morning and then
Again,
so in the
after
morning and
maybe
then at
after
8 a.m.
9.
I have class.
After 9? What about after 9 p.m. in the evening?
9 to 11, sir.
Yeah, 9 to 11 would be okay.
Okay.
Right, okay. Then let's do
Yeah.
like that. Right, okay. Then good night. See you all
Okay.
next.
Okay.
Right.
Thank you, sir. Good night.